Hello, my name is Chris Swindell, and I'm a computer science student at Tennessee Tech University. I'll be briefly covering my work on further optimizing an ultracold neutron spin dynamics simulation code following some of my previous work last year. As part of the overall UCN tau experiment, the simulation code I worked on is being used to help more precisely determine the average free neutron lifetime, or tau n, as labeled in the relationship on the screen right now, through its relationship through tau n's relation to the average lifetime of neutrons that leave a magnetic trap through means other than beta decay, which we've called tau non-beta, which is outlined in purple. Specifically, the simulation code I worked on was focused on helping determine the average neutron depolarization lifetime, which is outlined in green and as part of tau non-beta. The code I worked on simulates a single ultracold neutron, or UCN, inside a magnetic trap, keeping track of its spin and position as it bounces around inside the trap. Realistically, we'd like to simulate UCNs on the order of around 1 million to have useful amounts of statistical data. However, the code as it was when it was given to me took about 36 hours to simulate only 100 neutrons in one instance. Scaled up at that same rate, it would take around 40 years to simulate our goal of 1 million UCNs. Part of the reason the code is so slow is due to the complex calculations involved, of which there are hundreds in just one time-step iteration to determine a UCN's position and spin. I'll be using the flowchart that you're now seeing on the screen to reference the different versions of the simulation code I created during development. Last year, I tried optimizing the calculations themselves while keeping our simulation code in Python, as well as converting the code to a Python C++ hybrid using Cython, as shown in the portion of the flowchart outlined in red. Altogether, I was able to get our simulation code to run about 2.7 times faster than it did in its original form. But that still wasn't good enough for our purposes, as it would still take at least a decade to simulate a batch of 1 million UCNs. I decided that the best improvement would come from converting the code completely over to C++ due to differences in how the languages work. While accomplishing this, I also incorporated one of the techniques I used in Python known as cache variables, where I stored intermediate calculations as variables if they were used more than once, to save time that would be used performing the same calculations repeatedly. Combined, these two things resulted in a C++ simulation code that was about 88.5 times faster than the original Python version. The cache variable method netted a speedup factor of about 2.2 in Python, so if that were still assumed to have the same effect in C++, the conversion to C++ had a speedup factor of at least 40 on its own. Next, looking at the portion of the flowchart outlined in orange, I tried representing physical vectors as different types of data structures. Originally, I had used array objects out of convenience, but I discovered that representing physical vectors as either built-in arrays or structures nearly doubled the speedup factor again in both cases, with structures having a slightly higher advantage in our case, at an overall speedup factor of 168.6 from the original Python version. Until this point, data was being recorded to text files after a simulation was completely finished, so that it wouldn't count towards the runtime of the simulation. However, it would be more practical if data were written simultaneously, or at least intermittently, while a simulation would be running in the event of something like a computer or program crash to prevent a complete loss of data. To solve this, I tried using parallel programming, specifically multi-threading, to implement data recording simultaneously with a running simulation. While my method was successful, it unfortunately resulted in a degradation to our overall speedup factor, as can be seen in the yellow outline portion of the flowchart, at only about 91.5 times faster than the original Python version. As far as what needs to be done next, we think we've stretched the benefits of C++ as a language about as far as we can take them. Even though my implementation of multi-threading degraded our speedup factor, We've kept it in our current code because of the necessary function it provides of simultaneous data recording. Different multi-threading implementations or other parallel programming techniques are still likely our best chance at further speed increases, and as such, those will need to be studied more in depth. In the end, we now have a Neutron spin dynamics simulation code that is now 168.6 and 91.5 times faster in sequential and parallel versions, respectively, than it was in Python. That's all I have. Thank you for watching.